Welcome to this class. In this class, we'll study about torsion of a shaft having circular cross section. Okay, so I have already drawn a figure over here. So to study the torsion of this particular shaft, let us consider this particular shaft as shown in figure. So let the length of this shaft circular cross section, this length is L. The radius is, let's say radius, let me write this here. So L is the length of rod or length of, we can even call it a beam, length of, let's say, rod. Capital R is the radius of rod, as we have assumed that it has circular cross section and it is throughout the length, it is constant. So this is the radius of rod. Okay, so what is meant by torsion of this particular rod? So as shown in this figure, we have two ends of this rod. So let's call this end as left end and this as the right end. So let me write these conditions here. Left end of our rod is fixed to certain support and right end or right cross section is free. So in fact, if I draw a short diagram, a brief side view of this particular rod, so this end, left end, is now fixed. This has circular cross section. Its diameter is 2 times r. This is free end of this particular rod. This length of this rod is L. And now for the bending, in the last class we have studied that if we apply a transverse load at any point on the span of this particular beam, it is subjected to bending moment. So it will bend and it will have certain depression at each point, right? So similarly, if I apply a couple at any point on the span of this particular rod, even you can call it this as a beam, cantilever beam, then it is going to twist as this end is fixed. So due to transverse load, it will bend. Due to the couple, so as we are applying this couple, let's say for example at the free end we are applying this couple, so basically we are twisting it. So we have fixed this particular end. So let me draw like this. This end is kind of fixed end and we are applying certain kind of couple in this particular direction, so it is going to twist. So if I consider, so let us consider a small shell. So let us assume that this is a small shell, which is a part of this particular entire rod. So let's say this is capital R is the radius of rod. So whatever I have drawn in this particular, let's say figure A, is this one. So this is having a shell of diameter 2r. So this is particularly small r. It is just a shell. Let's say this O. O is the center of this right end cross section, and this small r is the radius of shell. Let us consider a point. So let's say this is point A and this is point B. So AB is a line on shell of radius r, radius smaller. So as we have assumed this particular shell, we have taken first a simple line AB. Now, as we have subjected this rod to twisting moment or kind of a couple, so it is going to produce exactly equal amount of couple at free end in opposite direction. So basically, you are doing this thing. So if you draw a free body diagram of this particular rod, so you're applying a couple in this direction, it is going to produce a reverse couple at fixed end. So basically you're twisting this rod, and due to twisting, and as A point is now fixed because this support, left hand support, is fixed to certain rigid support, right? So this is not going to move at all. So what happens now then? So if you twist this B point gets shifted due to twisting, and let's say it assumes a position A B dash now. Now this A B dash, the same line on shell of radius r. This is before twisting, so that's why we can call it as original, and this is after twisting. This is after twisting. So let us say this angle by which this B point is twisted is theta. So this is angle of twisting. This is called angle of twisting. Okay. And as you can see here, this line AB is also shifted by small amount of angle, and this is something different. So let's call this angle as phi. So phi, or you can call it as a phi, is the angle by which AB got twisted. So these are different angles actually. So this is phi is not called angle of twisting. This theta is called angle of twisting. Now we have to find the relation between this phi and theta. So now if you look at B dash, this B dash is an arc of this particular right hand cross section, circular cross section. And you know arc length is given by radius times angle, central angle theta. So from here, B dash from right hand cross section, I can write B dash as R times theta. At the same time, if I look from the line AB perspective, if you find the length of this particular arc again, then for this arc B dash with center at A, because A being on a fixed end, it has not shifted at all. So that's why A being a center and AB being original radius, now AB dash is a shifted one with angle phi, then the length of AB dash I can approximate BB dash, I can approximate as length of AB, original length of AB times small angle phi, which I can replace as L times phi, L times phi. So from here, I get an expression or relation between theta and phi. What is that relation? So it is B dash. So this R times theta equals to L times phi. Or in simple language, I can write phi is equals to R theta upon L. So this is important relation for us. Phi is equal to R theta divided by L. Okay, all right, no problem with that. So we have derived the relation between phi and theta, and this phi is basically what? This is nothing but a shearing strength. This is nothing but shearing strength. So look at this particular. So if you know the meaning of shearing stress, if you assume similar condition, so let us consider this square block which is fixed to one end, and if you apply a tangential force, it gets shifted to certain new configuration like this, and the angle by which it gets shifted is known as shearing strength. Similarly, it is just kind of in 3D, and our circular cross section, these points on circular cross section are getting twisted and assuming new positions, so we can call this phi angle as a shearing stress. Now we know the relation between shearing strain, shearing stress, and modulus of rigidity. So what is that relation? So I can write modulus of rigidity as modulus of rigidity, which will denote by G. We can use different symbols because different reference books follow different symbols, but we'll follow G here. So modulus of rigidity is shearing strain. Let's call the shearing stress tau divided by shearing strain phi. Divided by phi. So from this, I can write this shearing stress equals to G times phi. So G times R theta over L. So let me simplify. So this shearing stress, let me write G theta over L times R. So this is important relation for us. So first relation, we have got a shearing stress in terms of small r, where the small r is a radius of any shell which is a part of this particular rod. And if you see here, this angle of twisting, it will be same for all shells, right? So capital G, moment of rigidity would be same. Capital L, length of rod would be same. So basically our tau max, maximum stress will occur when this R assumes maximum value. And where is it? So G theta upon L, and the radius, value of radius would be maximum on outer surface, and outer surface, the radius would be equal to capital R, which is radius of this particular rod. So shearing stress would be maximum on outer surface of the rod, and it would be zero at the axis, because when r equals to 0, means this radius becomes 0. So radius basically becomes 0 on the axis. So on axis, there will be no shearing stress at all. So as you go away from the axis towards outer surface, your shearing stress will go increasing and it will be maximum on the outer surface. Okay, so now we have derived the relation for this shearing strain. Now we'll derive the torsion equation. So exactly similar to what we have studied in bending moment, as the transverse load is responsible for producing bending moment in the beam. Similarly, a couple is responsible for producing twisting moment, and we are going to find next a twisting moment produced here. Okay, find that. So now again, we'll draw a certain diagram over here. So let us draw this diagram, small one. Suppose this is radius what we have considered, and suppose there is one. Now we have considered the shell particularly, right? So let us consider a shell over here. Okay, so this is a shell. So let's say this radius, sorry for this. So what we have assumed, so this is what we had drawn already. So this is shell of radius r. Now we have considered this small area. So this shell is having a thickness. So this thickness is equal to dr. So basically we have a large cross section area having capital R radius. In that we have considered small shell at radius r, and it is having certain small thickness dr. Now we have this shearing stress. Let me write this shearing stress. So this shearing stress denoted by tau is equal to g theta upon L times R. Now we'll find the twisting moment. So twisting moment, this shearing stress is produced basically due to tangential force, right? And so it will produce a tangential force. So how to find this tangential force? So this tangential force would be given by F equals to tau times small area dA. So I can find this tangential force equal to this tau. Let me write this as tau. What is the area of cross section of this? So this circumference times thickness. So as we are assuming a small thickness, how to find that area? Small area equal to circumference 2 pi r, this with certain thickness dr. If you have a large thickness, then you have to consider circle area of larger circle minus area of smaller circle. So even if you do it here, suppose A2 is a larger circle area, so it would be pi r plus dr whole square, and A1 smaller circle, it would be simply pi r square. So dA change in area, this is A2 minus A1. If you expand this out, pi square this term, r square plus 2r dr plus dr square minus pi r square. So this pi r square gets cancelled. So it would be 2 pi r dr plus pi times dr square, and dr thickness being very small, the order of this magnitude would be very small. So we are neglecting this and we end up the small area having an expression equal to 2 pi r dr. That's why for small thickness, we take this differential area. We call this as a differential area as 2 pi r dr. So I'm going to multiply this 2 pi r dr. So what I get here? So this is g theta over L tau expression multiplied by r. Here we have one more r. So let me write this as 2 pi r square dr. 2 pi r square dr. Okay, now I have found the expression for tangential force. Now this tangential force will be acting in the tangential direction to this cross section area, and it is going to produce a twisting or couple about this center. So let us find this twisting moment. So let us find twisting moment. Now twisting moment T, it is denoted by capital T. So mention this difference between these symbols. This is tau. It is pronounced as TAU. This is tau and this is T simply. twisting moment. So how to find a twisting moment? Twisting moment is basically a couple, and couple is found as multiplication of uh, this tangential force and moment arm. Okay, all right then. We'll multiply. So moment arm is equal to radius. So this is equal to g theta over L. This is 2 pi. This is tangential force multiplied by. So let me write this as a tangential force multiplied by r. So let me write this as tangential force. Sorry, I have already written this down. So let us write down r square dr multiplied by r. And now this is due to small differential area, and we have to find the entire twisting moment. Then we have to integrate this. So we have to integrate this over area of cross section. This area, this A on which we are going to integrate, this is area of cross section. This is area of cross section. So basically, though I have written this area over here, basically we are going to integrate for this radius because we have kept this radius as a variable over here. So purposefully, for the sake of understanding, I have written the area part here. So this is, we are going to integrate this over area of cross section. The simply means for the area, the entire area. So what we get here, this t equal to, okay, so let me write the integrand first. So g theta upon L, this is 2 pi r square r, it would be r cube times dr. And now we have to put the limits for this variable radius. So r, it starts from 0, so we have considered a solid rod, to outer surface we have capital R. So let's integrate. So these are the constants. We can take it out because this theta is the twisting moment. The twisting angle, which will be constant. Okay, take it out. G theta upon L, 2 pi, I have taken out. Integration of r cube is r raised to 4 upon 4. You have to put limits r equal to 0 to r equal to 4. Sorry, r equal to r. Okay, what you get? Simplify these terms and put these limits. So you get g theta over L and pi r raised to 4 upon 2. Okay, so we have got the relation for twisting moment. So T, it depends on what? G, modulus of rigidity, twisting angle theta, length of rod L, radius of rod capital R. So this is what we have obtained so far. So the quantity, this quantity pi r raised to 4 upon 2, this is called a polar moment of inertia. This is called polar moment of inertia. So let me write this as J, where this J is equal to pi r raised to 4 upon 2 and called polar moment of inertia. Polar moment of inertia about axis of rod, about axis of cylindrical rod, you can say that. Okay, so what we have got here, so we have to finally relate these three terms here. So I have got this relation. You can see this term here, g theta upon L. You can see this term g theta upon L. So I can write g theta upon L is equal to, so first I can write this as tau divided by r. So this is tau divided by r, which is equal to this t divided by j. This is t divided by j. And this is what we know as an equation of torsion. Equation of torsion. So exactly similar to bending equation, we have this torsion equation where we relate the terms like modulus of rigidity, angle of twisting, length, shearing stress, radius, and twisting moment and polar moment of inertia. Exactly similar. So you would have seen in that expression over here. So if I write analogy over here for the bending part, so it would be m divided by m bending moment. Instead of bending moment, we have here twisting moment. Instead of polar moment of inertia, we just had simply moment of inertia. This tau, we had sigma bending stress. Here we have twisting shearing stress divided by this r is the distance from the neutral axis in case of bending. So it would be y equals to, here we had just E. Instead of modulus of rigidity, we had Young's modulus over small r, that radius was a different part. So this was the bending equation, exactly similar analogically we had here a torsion equation. Okay, so we have got this torsion equation. So finally we'll see a new term, and we have already seen the analogy, and see how to find this polar moment of inertia for the circular part in brief. Okay, so what we have got finally? So finally we have got this particular relation as tau divided by r is equals to t divided by j equals to g theta over L. G theta over L. So particularly if you look at this particular expression over here, so what it gives here, so I get T upon theta. T upon theta equals to Gj over L. Gj over L. And this particular term is called C, which is, what is that called? This particular term, like this is exactly similar to EI. This is exactly similar to EI. Okay, what this term is called? This is exactly similar to the term EI in case of bending, and this is called torsional rigidity. This is called torsional rigidity. So basically, what is torsional rigidity? Torsional rigidity is nothing but twisting moment per unit angle of twist. Per unit angle of twist. So you have got this particular relation over here. So couple per unit twist or twisting moment. So let me write this. Twisting moment per unit twist, per unit twist or twisting angle is called torsional rigidity. Torsional rigidity. And we denote usually by the symbol C, capital C. And it is given by what? C equals to, this is by the definition, twisting moment T per unit twist theta, and we have got the expression for this as a G modulus of rigidity times J polar moment of inertia for that cross section divided by length. So basically it depends on the rod. It depends on what it depends on. G modulus of rigidity, property of material. So it depends on material of rod. The polar moment of inertia, the expression for J for circular cross section pi r raised to 4 upon 2. So it depends on radius of rod, and again length. So in short we can write dimensions of rod. Dimensions of rod. So it depends on both material as well as dimensions of the rod. So if you take a rod of same material but of different dimensions, you can end up having different torsional rigidity. And if you have same dimension but different materials, then also you end up with having a different torsional rigidity of these particular rods. So finally, so if I simplify this expression for the rigidity, modulus of rigidity, so what I get here, this G upon L, and the expression for J pi r raised to 4 upon 2. So from this you understand this. If your radius is more, then your torsional rigidity would be more. So basically what is meant by more torsional rigidity? So more torsional rigidity means less angle of twist. You can see that expression and the relation here. Less the angle of twist, more would be the torsional rigidity. So if your rod is having more torsional rigidity, it will be subjected to smaller angle of twist. So if you want, in a particular application, if you want a small angle of twist, then your rod must have a larger modulus of rigidity. And how to get that larger value of rigidity, torsional rigidity? So to get that higher value of torsional rigidity, you should have the larger radius and smaller length. So similarly, if your rod is having small length, then also your C would be more. So R is more, we can call these rods as thick, and L is less, we can call them as short. Then these rods will have larger torsional rigidity. So thick and short rods have larger torsional rigidity, and vice versa. If I write thin and long, and if your rod is thin and long, thin means radius is less and long means length is more, then your torsional rigidity would be less. And if your torsional rigidity is less, then your theta is less. If you are larger torsional rigidity, theta is less. And if you have small, then theta is more. So based on this, depending on application, you can choose wisely for the dimensions of your rod. So this is about torsional rigidity of the rod. Okay, so now we'll briefly understand what is meant by polar moment of inertia of a circular cross section, and then we'll stop, and in the next class we'll discuss about torsional pendulum. Okay, so what is meant by, so let us draw a diagram for that. Okay, suppose this is the cross sectional area, circular cross sectional area. So in that, let us assume a small cross sectional area, again with having certain thickness. So fine. Sorry for this again. Okay, so we have this circular cross sectional area. So this radius is capital R. We have taken a small shell at radius small r having thickness equal to dr, again similar to what we have studied for this torsion. This is exactly similar. What is torsional moment of inertia? Torsional moment of polar moment of inertia. Polar moment of inertia denoted by J, it is integration of. So you have to consider the area of this particular shell. So area, this is basically, let me write as area times distance square. So this is basically area times distance square integrated over this particular cross section. So small area we have already seen, it is equal to 2 pi r dr. Okay, so we are going to multiply this with r square and then integrate over this thing. So this is what exactly what we have already done. This is 2 pi r dr, small area multiplied by distance square from the point of symmetry, which is equal to radius squared, integrate over the cross section. So integrate over this small distance dr. So we have already taken this particular expression here. So basically I'll write the definition over here. So it is actually r square dA integrated over area. So unit you can see here as r square and dA unit. So it will have a unit of meter raised to 4. So we have to integrate this over area. So small area I have already written. This is dA and distance square. So we have to add the contribution from all such differential small areas to contribute from the entire cross-sectional area. So we have to integrate this. So this is basically 2 pi r cube dr. And we have to integrate from r equal to 0. If my rod is solid, then I have to integrate from r equal to 0 to r equal to capital R. If you have hollow, then you have to integrate from r equal to r1 to, let's say, r equal to r2. Nothing else. 2 pi integration r raised to 4. This is r raised to 4 upon 4. Integration limit 0 to r. So if you again simplify, you get the expression exactly same. This is pi r raised to 4 divided by 2. This is what we called polar moment of inertia. So this is the basic definition of polar moment of inertia. R square times dA, integrate over the area. So that's what we used in the torsional expression. And let me write the final expression again. So let me write tau upon R equal to T upon J equal to G theta upon L. And let me write again the meaning for the final time. So this tau shearing stress at a distance r. This shearing stress is basically at distance r from axis. This is at position r from the axis. So r, I have mentioned already the distance from the axis T twisting moment, this T twisting moment, exactly similar to what we have studied in bending moment denoted by M. J, polar moment of inertia, there we had just moment of inertia, polar moment of inertia. G, modulus of rigidity of the material of rod, there we had Young's modulus, modulus of rigidity. Theta, angle of twist, and L, length of rod. So this theta over L term can be sometimes written as angle of twist per unit length. So twist per length of rod. So these are the meanings of these terms, and this equation is known as equation of torsion. Equation of torsion. So exactly analogical to what we have studied for the bending part, if we apply, suppose if we have similar a cantilever beam like this, and instead of applying a transverse load at certain position, if we apply a couple at certain position from this fixed end, then it is going to twist, and then we can see the stresses, shearing stresses developed in this particular beam, and this is the expression for those shearing stresses. And this shearing stress tau would be maximum on the outer surface where this R would be maximum, and it would be 0 on the axis where we can see the symmetry. So this is what about the torsion of a rod or torsion of a circular beam. So in the next class, we'll study about torsional pendulum.